Hey folks, welcome back to another video on this series on PyTorch. So the last time we saw how to create a model using the sequential API when all your model can be put in a single linear graph where you feed an input and the input goes into one layer and its output goes into the next layer and so on. So it's all sequential. Now we look at the thing that you will be using most of the time, which is torch.nn.Module. So this is the other way of making networks. And basically, this is the base class of all neural network modules. So whatever model that you see around has been subclassed from this. And all your models should also subclass this class. So basically, this gives you all kind of freedom that you need. Basically, all you'll do is you'll create a class for your model, and then you'll subclass it from nn.Module, and then this is the constructor where you define all the layers that you need, and then this is the forward method. So in this forward method, you can have multiple inputs. You can do different kind of cyclic graphs, and then multiply things together. Do basically sky's the limit. Do whatever you wish to, and that's what I want to show you how it looks like. So this right here is the documentation. I'll come to it in a bit, but before that, let me first just go ahead and open up VS Code and show you basically how to implement it. Okay, now that I have my VS Code up, let's begin by importing all the modules that we need. So I need torch, I need torch.nn, and let me import that as nn, which is the standard convention. And then let me also import um, a submodule from torch.nn, which is functional. It contains all the functions that you will typically use, like relu and all those direct activation functions and things like that. So great. No module named nn torch.nn.functional. Oh, I'm probably on the wrong Python version, so let me switch over to a different Python and let's try that. Give me a moment while I debug this issue. Oh, I realize that it's functional. Oh my god. It's 11 p.m. here, so please forgive me for this silly mistake. I was on the right Python version. Okay, great. So now that this has been imported, let's create a simple neural network, and the network that we will make would be the same one as we made before. So all the networks are basically classes. So let me call it class model, and this should subclass from nn.Module. So first you need to define the constructor, and this constructor should first initialize the superclass, which is basically nn.Module. So you need to initialize its constructor. We use super keyword for that. And now let me define some layers. So I'll define a couple of variables. So just like before, I create a linear layer and I'll create another linear layer. Notice last time we had two layers, or rather three layers, two linear layers and one relu. But here I can create a relu layer, but I'm just going to use the functional API for that. That's that. And then I also need another method, which is the forward method. Now this method defines what computation does your model do, or how the data flows through it. You don't need to do a backward pass graph because again, using autodiff, a backward pass will be created. So this is pretty seamless. So you define this forward function where I specify the input of my forward function. Also need self. And then now I just define the computation. So first I tell it that x would be the linear layer applied to the input. And then I'll apply relu to it. And then I'll apply the last final layer to it. And then I return x. Pretty straightforward. So you see, like I'm using the same variable to apply L1 in a functional form, and then I apply relu in a functional form, and then I again apply this layer in a functional form. That's it. So you see, it gives you a lot of freedom in how you want to perform computation or what you want your model to do. I can call in different functions that do different parts of the computation and so on. So sky's the limit here. But again, I don't want to go too in detail. Like I don't want to give crazy examples because that's not the point of this video. The point of this video is to show you how to use nn.Module. Um, all right, so that's our class. Now let's create a model by creating an object of this class. I create my model and let me show you what it is. Um, oh, ah, I had a typo there. So when I output my module, it tells me the variable name and what kind of layer it is. So if you have a complicated model, you'll have a bunch of variable names and a bunch of stuff about it. So that's basically how you create your model using nn.Module. Now let's say I want to let's apply it, like pass some data onto it. So let me first create some dummy data. Excuse me. Um, so I create a tensor. I apologize for that sneeze. And yeah, so I create a tensor, and all I need to call model.forward on A. So oh, I made a typo again. There should be X. Ooh, lots of typos today. Okay, so when I call model.forward, I get some result. Great. I don't need to call the forward function explicitly. I can just call model like this and it'll call the forward function. So you see the result. Now, once we get the result, we have some value. I can compute loss on it and I can compute backwards to get the gradients. So this makes life pretty easy. All I need to do is just get the compute the loss and do loss whatever the loss is dot backward, and autodiff will take care of the gradients. So pretty straightforward. Now you would ask me gradients of what? So we need the parameters of my model to compute the gradients. So there are multiple ways to access the parameters. One of the ways is calling the state dict. So when I call state dict, it gives me an ordered dictionary which contains all my weights. So you see I have L1 weight, I have L1 bias, L2 weight, L2 bias. So this dictionary contains, it's an ordered dictionary of all the weights of all the layers. Now, this is how models are stored in PyTorch. Models would have their class definition, and the weights are stored in this state dictionary variable. So I can save this ordered dictionary and then give it to you as my model weights, and you can just load it in. So this model.stateDict tells you to gives you the list of all the weights you have. Now I can always do load stateDict and load a stateDict that you provide me. So this is way. So the models have their class definition and the weights associated to them, and that's stored in the stateDict. Or stateDict shows you all the weights. Now I can also call model.named parameters. What that does is it'll show you all the parameters that are present, and by calling it, it tells me it's a generator object. So what that means in Python is I can loop over it. So if I do for I in this, now let's say I do print I, um, oh, to call it, I get basically the same information. So for each, so my parameters are basically the weights of my layers. So first I go to L1, I get its weight, then I get its bias, then I get a weight, and then I get a bias. So I can iterate through it using model.named parameters. Named parameters is because like these contain a variable name. The other way to access the weights could be I can just directly reference into them. So model.L1 and then I can do anything that I want with L1. So if I want to get the weight, I'll do the weight, and you can see I have been able to access the weight. Now let's say I wanted to override my weights, right? Put some new values to them. So the way I would do that is, let me create um, a tensor of the same dimensions, because we want the dimensions to be the same. So let's say create a bunch of ones, and I'll put them to be the same dimension as my original weight, and then I will do model dot L1 dot weight, and I assign it to A, or I assign it to be A. But before that, I need to convert them into parameters. So it's torch.nn.parameters of A. And now when I display, you see all my weights are 1. So I've changed the weights of my model. Now the main thing is, first I have created a bunch of ones, and then I assigned it to the weights of that layer. Before assigning, I did this thing. I converted them into torch.nn.parameter. So the weights of layers are of type parameter. Parameter is basically a subclass of tensor. That's why I could convert it. And all it does is basically, just think of it as a rule, like all model um, weights and biases are stored as this parameter type. So that's why every time it's said parameter containing. So this is just a data type which is subclass from torch.tensor, and to set the weights you need to convert it into parameters. So the reason for that is, in the module class there should be some distinction between regular tensors lying around, tensor constants, and parameters, or the weights of a network. So that's why the weights are parameters. That's a very minor distinction, but it's still a distinction. So that's one conversion that you need to do. I think that is pretty much it. There are like a couple of useful utilities. Now, the model that you create initially is stored on your CPU. Like all the computation would be done on your CPU. Now, if you want to put it on your GPU, you can pass in CUDA and your device index. That will take you to the device. Currently on this Python edition, I have the CPU version of PyTorch, so I can't. So if you have a model on GPU, if you want to make it you want to transfer it to CPU, you do model.to CPU. So that's how you move model around, and obviously it'll perform faster on GPU. But again, you have to take into account the overhead of moving model from um, your regular RAM to VRAM. That's one thing. Finally, let me show you a mode. So when you train, so I haven't shown you a training loop. I'll probably after at the end of this video like pull up the documentation and show you a regular training loop. But the training loop looks just as before as the previous video in the sequential API. Once you have the model, you do forward pass, you figure out what your loss is, you do backward pass, and then get the gradients and optimize it. Okay, but model gives you some efficient ways of doing things. Like once you have computed, or once you have done training and you want to evaluate your network, there are two modes that you can do. The first mode is put the model in eval mode. Now what that does is it still computes the backward graph, but in evaluation mode, the values of parameters like batch norm, etc. are frozen. Remember, batch norm, what batch norm does is it keeps a moving average. Or so while training, like it takes a moving average of like whatever your batch norm is, or whatever batch norm is for that feature, it keeps that average moving as you get more and more data. But when you're evaluating, you need to use the final average value. So what model.eval does is it freezes the batch norms and the layers like that, and then you only backpropagate through, you can only backpropagate through the other layers. So batch norm and states, all the states are frozen. So that's what model.eval does. Now I want to show you the output. And the other mode is model.nograd. So what, sorry, with torch.nograd. So when you are evaluating or doing inference, you don't want the backward graph. So you should disable the gradients, um, and then compute your to perform the inference. So lots of typos today. Right. So here you see I ran my model through this network, and my model output changed because I changed my weight dimensions. So let me put it back. Let's try this and do this. Oh no, that was correct. 10 1. That dimension is correct. Why is my output now 10 dimensional? Let me do forward. Let's see. Oh, I forgot. A is now something different. Let me go back and create A to be one dimensional object or zero dimensional, one comma one dimensional. Okay, great. So now that you see when I ran through, so what the issue was here, I created A again and I made it 10 comma 1. So there were basically the batch size is 10. That's why I was getting so many values. But now in the evaluation mode, I still get the backward graph, but with no grad, I don't get a backward graph. So that's one advantage. Also, if you want to zero out all the gradients, you can just type model.zeroGrad, so that zeroes out all the grads. So that's pretty much it. It provides all the useful utilities that you would need to create your model, and because you have all the freedom, you can perform your connectivity because you're defining how your model computes. You can construct anything. So sky's the limit. So with that, I think I'm done with the coding part of this video. I just want to show you some things from the documentation, especially a training loop. So let's go back um, to, so there's a nice help, the documentation file on modules is pretty good. It contains almost everything. Well, this one doesn't have, well, let me actually pull up the documentation and first go through things that I might not have talked about. The apply function, basically, let's say you want to apply a function to all the layers. So you can maybe modify their weights in a certain way, initialize the weights in a certain way. So you can call apply function. So torch.nn.init is something that you will use for initialization. Um, then there are like data types if you want to like work with um, float 16 and so on. I think the default is 32. Yeah, get parameters. You can work with, you can have modules within a module. So let's say a friend of yours supplied you a different module. You can just work it together, create a module within a module. So you can get some modules and that kind of stuff. Um, Directly convert into float 16. Um, yeah, nothing too useful. Parameters gets you the list of parameters of your network. Register forward and backward hook is something we'll talk later when we maybe discuss about pruning. I don't know if we'll get to that, but this is some advanced functionality and it keeps on changing. That is, I guess that's it. Yeah, two transfers your module into CPU, whatever device you want. All right, and you can also directly train your network. So just like there was an evaluation mode, let's say you from evaluation mode you wanted to go into the training mode, you will call model.train. So so that's that. Let me open up a training loop. All right, let me show you a training loop. So here's another two-layer network with two linear layers. So and this is the forward pass. Something happens. And basically some test data is created and then the model is instantiated, and then here's our loss function, here's our optimizer, then we loop over some number of epochs, perform prediction, compute the loss, um, basically start with zeroing out my optimizer, do a backward pass, step my optimizer. So the same loop that you saw before. You compute the loss, do a backward, and then you step the optimizer. So that's how you use model, and like I said, sky's the limit. So I think this is a good endpoint for nn.Module, and we'll keep on keeping on more cool things about PyTorch. So right now we've just scratched the surface. I hope you guys liked this video. And again, all this code is on my GitHub page. The link for it is down below. And see you guys again next time. All right, bye.